Well, how are you doing? Okay, this is going to be a bit of a stinger for our opposition. The name of this video is Origins of the Globe Earth's Radius Value. Now, I've been in this debate at this point 7 years, and there's a few who've been in it a bit longer than me, as far as this part of Flat Earth, the wave of debates goes. And in all those 7 years, at any point where someone especially in the past recent years when we've all gotten more information, when someone is looking for the origins of the globe Earth's radius, our opposition can never actually give us that. They used to state Eratosthenes, but Eratosthenes measured a flat plane. And then he added or afterwards. That's the story. But he had to measure a flat plane first, 500 miles of flat with elevation angles. Used to be Al-Biruni, but the horizon's not geometric, so that's the end of that. So where does this radius value come from? If you'll notice what I'm calling it is a radius value, because it is a mathematical value, a calculation. It is not a measurement, but it does come from a measurement. And this is what I'm going to show here. Now, I've recently showed this on Nathan's Flat Earth Debate Show in the past few weeks. I didn't show all of this, but I went through the calculations of it and I explained it. And I've explained it since then several times, or one time fully, but I've been speaking about it. But I want to make a video here now. I hope it won't go on too long. And the reason I want to do it is I want to give people out there the knowledge of what I'm talking about, or the information, give them the information connected to what I'm talking about. So hopefully this will help. Okay, so this here, this diagram here, this is the most important part of this whole video. And why it's the most important part is because it's showing the horizon and the sun above the horizon, and you as an observer looking at it. Okay? Because this is what we see in reality. Although this is a diagram, in reality, this is the view we see. Our opposition are constantly giving us, for all these years, orthographic diagrams, which is side-on view. But we don't view anything side-on. We only view things in the frontal perspective view, like this. So even though this is only a diagram, it's still far closer to reality than any orthographic diagram. Because as I said earlier, I'm 7 years into it, and I have never seen a diagram that's connected to the globe or supports the globe or has anything to do with the globe Earth model without it being orthographic. They can never show us this perspective frontal view. They can never show us this, because this is reality. And in reality, this is how we see things. And in reality, if I want to measure from my position the elevation angle of the sun, I have to measure from my point using the mean sea level here, using a horizontal, that as my horizontal. I can then use my zenith with that horizontal as the 90, take my angle to the sun, and know, let's say I use the lower limb here, and know that between this lower limb and the horizon that there is whatever angle. But this area here between the horizon and the lower limb, this is my elevation angle to the lower limb of the sun. So I have the horizontal, which is mean sea level. I have my angle to the lower limb, and then I have the zenith from the GP point of the sun up to the sun. So that creates a right angle triangle, right? That's how you take an elevation angle. This is what you see. You don't see anything in orthographic view. It's impossible to see in orthographic view, because orthographic view shows you the side of your own head. It shows everything side on. So you can never see that way. You can only make a diagram and try and depict things that way, but you can never see that way. You only ever see like this. And that's why this is so important. And that's why our opposition for years keep on showing us orthographic diagrams, because the model they hold to their chests is an orthographic model. It's a mathematical model. Orthographic, it's purely mathematical, it's purely descriptive. It is not reality. It can't be. It's impossible. You can't buy orthographic binoculars, or glasses. You can't get a prescription for orthographic glasses. Can't do that. You can only see in this frontal perspective view. That's it. So, what we must do first is we must define what elevation is. That's the first thing, right? So, we go here, right? It says here on this that altitude is above a point, right? So, altitude is air pressure. It's connected to air pressure, and it is basically, it's like your altitude is based on the air pressure you're at. So, yeah, your altitude is above a point, but it's more to do with air pressure, right? If you want about altitude, it's the altimeter measures air pressure. That's air pressure. But elevation is always above sea level, always. So all elevations are taken from mean sea level, right? Always. So if we go to here, we have elevation, feet above sea level. See, this is a mountain here, and this is all the gradient of elevation at different points above sea level, right? So it's all taken from sea level. All this elevation is taken from sea level. So if they want to take an angle to here, then that angle will come from sea level. But that angle has to use a 90 degrees. So sea level has to be the horizontal. That's why when they're using a marine sextant, they always have to do height of eye correction to correct from what is an obtuse angle between the observer, the horizon, and the object. I'll just go back to here to show. The observer, the horizon, let's say this person's up on the beach, observer, horizon, and object. But that's an obtuse angle. They need to correct that to make it a right angle. And then they have the horizontal. They correct it down to sea level here. So then they're using the horizontal of the sea level. They couldn't do that if the sea was curved. It wouldn't work. They need the sea to have the mean sea level. That needs to be horizontal. The earth needs to have a horizontal baseline for elevation angles with a sextant to work. It can't work any other way. And that's why our opposition have to use tangent planes. And the tangent plane, as I have made a video about, and I asked the question, how big can a tangent plane be? And I had every one of them on the globe side. They all said the same thing to me. It can be any size you need it to be. There's no maximum size to a tangent plane. So they're tangent planes which will touch a circle at one point geometrically. Their tangent planes can be as big as they need them to be. And they need tangent planes because they can't believe they're taking elevation angles and using a curved surface. They have to believe that they're taking elevation angles using a tangent plane, but it really is curved. So it's all backwards psychology that they're doing to themselves. And the fact that they even mention a tangent plane means that they're instantly admitting that this process cannot and will not work on a curved surface. So as soon as one of our opposition mentioned a tangent plane to take an elevation angle, that means they're stating that it can't be a curved. There can't be a globe. It can't be curved because to do what they're doing, they require a tangent plane. It just doesn't work any other way. And the tangent plane will be the measurement. They're not measuring on a curve, they're measuring tangent plane. And then after that, they will take it from the tangent plane point, which will be touching a circle at one point, and they'll then bring it into the middle of that circle, that same exact angle, and bring it right down into the middle of that circle, which is a hijacking of the celestial sphere model, but that's what they do. But so they're using one flat plane to take the angle from the surface, and then they are pre-assuming that tangent plane that they pre-assumed was touching a circle or a sphere at one point is then being brought into the center of that sphere or circle, and that angle is being brought into it with it. So it's all mathematical self-delusion. That's what it is. But the whole point why I'm stressing about elevation is that elevation is always off sea level. So all elevations off sea level and all elevation angles require a horizontal baseline. They are oppositionally emitted when they state that they're using a tangent plane. They have to, because it needs a horizontal. So elevation, here we are again, measuring relief and elevation. Elevation above above sea level. Here we are, right? Right. So this is from here to here. That's the elevation of the mountain, right? That's what it is, sea level, right? Here we are again, 700 foot above mean sea level. This helicopter, 300 foot. This house above mean sea level. There's mean sea level. So mean sea level always has to be a horizontal. It's always treated as a zero horizontal baseline, always. And all elevations are taken from that point. Right? This is important. Right? I just want to go to here. Right? The next point. So give me a line. So here I'm going to put a line from here to, let's just say, down to here. So let's say there's an observer, right, taking an elevation of the full of this mountain, right? So that elevation will be angle will start here at sea level and go to here, right? If they're taking an angle, an elevation of that mountain with this angle, right? Let's just say, I'm just going to use what they show here now. They could be obviously further away taking this angle and take angular size into account and blah, blah, blah. But the point is that this is the angle they'll take, right? But then, see here, this will become their zenith, this line here, right? And their zenith angle then will have a distance, a zenith distance, let's just say. So the zenith distance here would be from this arrow, the top of this arrow, to the tip of the mountain, this horizontal, this serrated horizontal line. So zenith distance is always horizontal. It's always a horizontal distance. And that's how how minutes of degree become nautical miles, because the minutes of degree of this angle, let's say this is whatever minutes of degree or whatever angle, right? It doesn't matter. Let's just say it's a 45-degree angle. It doesn't, right? It's easy. So that would be 2,700 minutes of degree. That means that the zenith distance, right, the co-altitude, let's just say for it, but this is not a star, so but we'll just pretend up here as a star. Co-altitude zenith distance is 2,700 minutes of degree. So that will be transferred then onto from this straight horizontal here, because it's a horizontal distance, straight down to become a distance along the horizontal that is needed for the elevation angle in the first place. So then that becomes 2,700 nautical miles, right? That's how it works, right? And that would be between the observer, let's just say the GP point. So I'll just get another, let's see, right, I'll just get another tables quickly now. So let's just say, right, let's just say this is the GP point here of a star. So you have this being the zenith angle, right? That will be the zenith distance here, straight line between the co-altitudes. And then you will have, then that will become, because it's, let's say it's 2,700 minutes of degree, that then becomes a distance, horizontal distance, using mean sea level as the zero baseline to the Earth, as of 2,700 nautical miles between what would be the observer here and the GP point of, let's say if we say this is a star, right? So, and this then is the zenith from the GP point to the star. So then you're creating basically a box with two right angles. You have your elevation angle, which is a right angle, but then you also have a depression angle coming down here, which is your zenith angle from the observer's point of view. Right? But if you have someone else up here, then from the star's point of view, it's a depression angle. But you're just basically making two right angle triangles within a box or rectangle. That's what you're doing. Okay? This is important, right? Here we are again. What's the zenith distance here? Now this is the celestial sphere model, which is flat Earth model. So don't worry about this arc. This is only a way of orthographically, because this is orthographic as well. Celestial sphere model is an orthographic model as well, but it's a flat earth orthographic model. And all this is showing is the arc. That arc there is a way of depicting, right, the use of angles from the frontal perspective view in an orthographic view, right, using the arc scale, right, of the arc scale of the protractor, right. So what is the zenith distance here, right? So let's just get another line. What's the zenith distance, right? So the zenith distance is that, isn't it? That's the zenith distance from the star to the observer zenith. So if this is the observer zenith, and that's the star, right? So let's get another line. So this would be the star's GP point down here. So then you have two right angle triangles again, right? You have an elevation angle, let's say this is the observer, up to the star. You have zenith angle here. So you have an elevation angle and zenith angle, right? This zenith distance that they're showing here, this is the zenith distance, this horizontal line across here. That zenith distance then becomes your nautical miles distance between observer and GP point. That's how that works. So horizontals are always, 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 always necessary, because you have to use 90 degrees, which means you need a horizontal and a vertical to take an elevation angle. That's what's required. And when you're taking elevation angles to the stars or any celestial bodies or any elevation angle to anything, you require a horizontal baseline between the observer and the point that you're taking an angle to, point below that. That has to be a horizontal. There's no way around it, right? This seems like, I know you're probably thinking that we know all this, yeah, but the problem is that this is part of it. It'll become, the reasons why I am sticking on this so much will become more prevalent in a while. So even our opposition, the point is, even our opposition understand that they need a tangent plane to take an angle, because they understand they need a 90. You can't take an elevation angle just by taking a zenith angle. That's not an elevation angle, because you still, to know your elevation, you have to do what? Your elevation angle has to reference what? Well, it has to reference, where are we? Where's the, has to reference this, sorry. Find it again. Has to reference this, right? The horizon. So your elevation angle has to reference the distance between the horizon and the celestial body, that angular distance, right? It's not, right? That's what it has to, or it's the angle there. That's what it has. That's how it's referenced. So our opposition talk about how they can just take a zenith angle to a celestial body, and that is somehow like that. This zenith angle from here is somehow the elevation, but it's not. That's to say that is totally dishonest, because the elevation angle is going to have to be subtract, like, so whatever your zenith angle is, to get the elevation of the star, you're going to have to use a horizontal and a horizon, mean sea level. You have to get the true elevation of the star at that time. Whatever star it is, the true angular elevation of the star, and not the actual true elevation, but the true angular elevation of the star at that particular time, you require a horizontal and you require an horizon. You can't do it without a horizon. So you need a horizontal and a horizon. A zenith angle is not, because I've had our opposition trying to tell me this, that they can use just a zenith angle to get an elevation angle. They don't need the horizontal. Yes, you do. You can't do it without the horizontal. You can't do it without the horizon. So this is important, and it'll become more important soon, right? So sorry, go back to here. Right. So we've established what elevation is. We've established to take an elevation angle, you're going to need the distance between the horizon and the celestial body in angle, right? To do that, you're going to require to use mean sea level, and that's required to be your horizontal. Your zenith is your vertical, and mean sea level is your horizontal. And mean sea level is the elevation through any landmass as well. So that horizontal baseline, that's what you're using. Because if you're taking a 45-degree angle to a celestial body, it means it's 2,700 nautical miles away from you. That means it's very likely going to go through some landmass in the process, or it might even be ending at a landmass. The point is that that landmass has to have a horizontal baseline, and that horizontal baseline has to be mean sea level. Mean sea level has to be a horizontal baseline for this to work. It doesn't work any other way. So we just go to elevation angle, object, line of sight, observer, horizontal line. That's an elevation angle. This is what an elevation angle is, right? Here we are again, right? This is a depression angle. See, horizon, horizontal. Ground, horizon, horizontal. Elevation angle, right? So what would be the zenith? The zenith here would be a line up here, and that would be the zenith distance along here, right? So there you go. Elevation angles require, and zenith distance and depression angles require the use of 90. Requires a horizontal and a vertical. Can't do it without it. Right? Elevation angles. Right? Angle of elevation, object, line of sight, horizontal. Requires it. That horizontal is what? That's the horizon. So your angle will be the angular measurement between here and the object. So between here and the object, that's going to be your angular measurement. There is angle of elevation from a person's eye line, using just a horizontal from a person's eye line. They have a depression angle to the cat and an angle of elevation to the plane, right? But it needs, none of these things can happen without the horizontal line. It can't happen without that. It's impossible. Here we are again, another horizontal. What is the zenith distance here? It's going to be from here across to here in a straight line. Or if you want to extend this arrow up the way, it'd be from here to the sun over here. That's straight line. That's your zenith distance. Zenith distance is a horizontal distance, not a curved distance. It's a horizontal distance. It's only been shown as a curved distance at times when they use the celestial sphere model. And that is then hijacked by the globe and turned into the globe's Earth's surface. But it's all orthographic nonsense. We don't view things orthographically. And we can't take an elevation angle to anything or a depression angle without the horizontal. And elevation angles require mean sea level for the true elevation of, well, if you're going to do elevation angles close to sea level, you're going to use sea level, right? If you're using a marine sextant, because that's what most of the time they'll do for celestial bodies, right? If you're obviously up a mountain, you can use an artificial horizon, or if you're in an airplane, you can use a bubble sextant. But this is another thing. The bubble sextant, right, the artificial horizon, and the Mariner sextant with the height of white correction, they all establish horizontal. So when someone in our opposition says, because they keep saying it, that level is not horizontal, yes, it is, because the bubble sextant wouldn't work if level was not horizontal, because the bubble sextant requires horizontal, because it's using the zenith of the pilot or the navigator on the plane that's using it as the vertical, and it then creates the horizontal with the bubble. The bubble level creates the horizontal, and that horizontal becomes the zenith distance. So it has to stay horizontal. It can't just be a little horizontal. It has to be whatever length the zenith distance is, whether it's hundreds or thousands of miles. So how could level be from the center of the Earth, of a globe Earth, and be a curved situation when level needs to be horizontal for the bubble sextant to work? complete and utter nonsense. The point is that to take an elevation angle to a celestial body at sea using the marine sextant, or to take an elevation angle from a mountain using an artificial horizon, or to take an elevation angle to a celestial body from an airplane using the bubble sextant, you require the horizontal. And that horizontal line stretches from the observer to the GP point of the celestial body. That's how it works. So it doesn't matter if it's along sea level, if it's up a mountain, or if it's from an airplane. It has to be a horizontal line. So here we are again, same thing again. The zenith distance. What's the zenith distance? There's the zenith. There's the zenith from the GP of the sun. What's the zenith distance? It's going to be this line here. It's going to match this line down here. That's how it works. It can't work any other way. It's impossible. Same again, horizontal, angle of elevation, line of sight, object. Right, that's just the angle of depression. Recording, look, horizontal distance. If this here was an observer taking a zenith angle up to something up here, then that would be the zenith distance from here to here. It's a horizontal thing, horizontal distance. Right, and we're back to that. So now the nitty gritty, right? So how did they do it, right? How did they come up with this calculation? Well, this is how it works. I'm not going to show orthographic view here. I'm going to show what happens in reality, right? So if this is the GP point of Polaris here, and this is an observer, right? The closer the observer is to the GP point, the higher Polaris will appear to be in the sky, right? So the angle to Polaris for the observer here will be, let's just say, a pretty high angle, right, to Polaris here, right? As the observer moves back, Polaris will appear to drop in the sky. So when the observer moves forward, closer to the GP point of Polaris, Polaris appears to rise. When the observer moves back south, so when they're going forward, it'll be due north. When they're going back, it'll be due south. Away from the GP point of Polaris, Polaris appears to drop in the sky. And this is all recordable with angles, right? So from the observer to the GP point here, that line here has to be a horizontal. It can't not be, right? We don't observe and take angles to Polaris orthographically. We take angles to Polaris in the perspective view, which is what this is. So Polaris will rise and fall depending on the position of the observer. But the line between the observer and the GP point will always be a horizontal line, because if they're doing this at sea, then they're going to be using mean sea level, right, between the boat here and Polaris, right? So when they're taking an angle, they'll be taking an angle to Polaris, and it'll be in height of white, and the other angle will be going to, let's say this is their horizon, and then they do height of white correction to give themselves a 90, and then they have their angle to Polaris. But there'll be a horizontal line between the boat and the GP point of Polaris at all times, right, when they're taking an angle to Polaris. So it's always going to be a horizontal line between the observer and the GP point of Polaris, always. So what they did is they took this perspective view, and they found out that when they get back far enough, right, let's say they go back way back, right, Polaris ends up being down here, right, on the horizon. And at that point, they will have amassed, right, they're going from 90 degrees when they were at Polaris's GP point, Polaris is at their 90, to back here to the equator where Polaris is at their 0. So Polaris was at their 90 when they were in here, right? But when they came back out here to the equator, Polaris appears to have dropped to 0 due to perspective. That's all it is. There's no error curve involved, because that line on from the boat for mean is using mean sea level. It's a horizontal, it has to be. So when they're taking this angle to Polaris, just when it's when they're a couple of degrees away from, or when they're, let's say, 180 miles away from the equator, Polaris is going to be 2 degrees above the horizon kind of thing, but notwithstanding refraction, just what it should be, let's just say, going by that calculation. So it's going to be 2 degrees above the horizon here for the observer when they're 180 miles from the equator. So that means that there's this much distance, right? Like well over 5,000 nautical miles distance between the observer and the GP point of Polaris, and that distance is measured in the horizontal, right? That's 5,400 nautical miles. So why is this so important? I'm going to use this. This is the Gleason's map, so but it has the latitude and longitude grid on it, so enough. So I'll show it with this. So if we take a line, say annotate line, and we go to the center here, let's say that's the GP point of Polaris, and we come out to the equator here. Right, where's the equator? Yeah, there it is. Right, yeah, that's the equator. So what they did is they knew that anywhere on the equator, it's going to be 5,400 minutes of degree of measurement to the GP point of Polaris. They knew this, right? And they knew that measurement was going to be a horizontal distance. So they knew that if they doubled that and put a person here and another person over at the other side here, at the other side of the of Polaris here at the equator, sorry, this is it. Then that would be 10,800 nautical miles. And then if they added on the same again at either side, so they added on another 5,400 here, so that'll make a 10,000, that'll give them a 10,800 nautical mile distance from the GP of Polaris to 90 degrees south, and another one from the opposite side, from the GP of Polaris to 90 degrees south again. That gives them 21,600 nautical miles, which is 21,600 nautical miles of a straight line. And what did they do from there? Well, if we go back to GeoBra, right? What they did is this. So let's just say this line here represents the 21,600 nautical miles. So if I just get a circle with a center, and I just go to here, make that out, right? If I just get a line, where are we? Segment that line. Go from here to here. Let's just say, well, it doesn't really matter. Now, so if this line here, I just change its color, just to make it a bit more viewable. I change the color of this to green, right? So if this line here represents 21,600 nautical miles, right, of flat horizontal measurement, right? If you then take this and turn it into a circle, it becomes this, let's just say, right? So they took what was a frontal perspective view, right? If I just go back to, where is it? Back to here a sec. They took this, right, and the measurements that were made using this view, right, and they turned it into a circle. So they had measured 21,600, they knew that they could have 21,600 nautical miles of horizontal. Basically, if you want to treat the latitude and longitude grid as a circle, then that would be the diameter of that circle. So they have 21,600 nautical miles. They turned that into, they took that, put it into orthographic view like I'm showing here, and turned it into a circle. So when that happens, we go to the calculator here a second. So 21,600, right? 21,600. So you want to get the radius of that. So you're going to divide it. So what you're going to do is divide it. So divide it by 3.14, right? Equals 6878.98 and change nautical, right? Nautical miles of diameter. right? So now, even though that can't be a diameter under these circumstances, I'm not going to go into that. I'm just going to use the number, right? So, because it's just maths, you can do what you want. This is the beauty of maths. So then they divided it again. So then they have a diameter that they took from a 21,600 nautical mile circumference that they made up out of a 21,600 nautical mile horizontal measurement. That's what they did. And they've got to the point of making a diameter of their circle. They then divide that again, right? Divide it again by 2. Gives them 3439.49044 and change, right? In that would be a nautical mile. That would be a nautical mile calculation, but that is not correct because, well, I say it's not correct. You can have a nautical mile. Obviously, that can be a nautical mile radius here, right? But they didn't want it as nautical, but that, like, of a circle, you can have a nautical mile radius, right? But the problem is that what they did is they converted that to statute miles. So when we convert that, so if I go to convert length, nautical miles to miles, convert. 3958.094915257070064. So that's 3959.094915257070064 statute miles. And they rounded that off to 3,959. Rounded it off up the way to 3,959. And that's where their radius came from. Their radius came directly from flat Earth elevation angles to Polaris that were taken using angles that measure perspective, because it's a perspective measurement. So they hijacked perspective to come up with their radius. And that's all they did. And after that, all they needed was that and the angular size of the sun, and the whole rest of the heliocentric model fell into place. That's all they needed, right? And the angular size of the sun is a kind of a separate point, which I'll probably make a video on. But because they hijacked perspective, this means that their orthographic model here, right, is orthographic. So there is no angular size change, there is no visual effects, there is no perspective. It's all orthographic. So angles and perspective do not exist on the globe model. They only exist in reality because we're not on a globe. You can't have an angular size to the sun on the globe Earth model because the globe Earth model is orthographic. There is no angular size change. It's orthographic. In reality, all angular size measurements, right, are taken in this view. This is reality view, right? What they show is orthographic. What we see is reality view, which is this, which is the horizon and the sun. We don't see side on us looking at the horizon and the sun, and the horizon being curved down the way, and we put a tangent plane on and all this other absolute rubbish. We don't see any of that. We see perspective view. You can't view anything orthographically outside of a diagram. It can't be done. No one can take an orthographic photograph. You can't get orthographic binoculars or glasses. You can't buy orthographic sunglasses. You can't have an orthographic windscreen to your car. It doesn't exist. So everything they're after doing is all based around the hijacking of this view. You can't have elevation angles on a globe Earth. You can't have angular sizes on a globe Earth. You can't have any visual effects on a globe Earth. You can't have a mean sea level that has to be horizontal on a globe Earth. But in reality, we do have all those things. They back calculated a radius, and from that radius, right, from a hijacking of flat Earth elevation angles, from that radius, right, and taking an angular size to the sun, right, angular size to the sun, there's no such thing on your model. It doesn't exist on the globe model. But those two things is all they needed, and they created the rest of the heliocentric model from there. So I'm going to leave it now. It's just 40 minutes long of a video. I know there were some parts I had to labor on, but it was very important for people to understand what is reality and what is not reality, and what they did and what they didn't do. I guarantee you not one person in our opposition, will be able to come up with an origin to their radius value. But we can come up with it because we know where it came from. It came from this view here. Something you don't see on a globe. You can't see it on a globe, because a globe is orthographic. So every view, if we lived on a globe, has to be orthographic, because their maths are orthographic, their maths dictate it. So don't leave them talk you around or want to conversate about any nonsense. Their globe is orthographic, their maths are orthographic. There is no way out of that. That is the globe model. So angular sizes, visual effects, anything like that, perspective, angles, none of these things can exist on a globe. That's the end of that. Thanks for watching.